So I can actually code into what can we do with data when we talk about CI/CD. We said we want a repeatable, reliable process. For data, we want a process that is reproducible. We can reproduce the same result of specific data. And we're able to reprocess. So if we want to go back to a previous time of how the data looked like, we can always do that and change the logic and reprocess, recreate something different out of this data. So combining the previous data with the new logic. So this is one. Second thing, we want to automate everything. For that, specifically for data and ETLs, we have orchestrators. If you work with orchestrators, give it a thumbs up. There's a lot of great orchestrators in the market. You have Daxter, you have Airflow, you have Kubeflow. There's a really good list of orchestrators in the open source world. Third thing is version control. So version control in data means version control for my table and version control for my bucket or my repository. So if I have a repository that holds multiple tables within it, I want to be able to version control that repository that holds multiple tables. So I want to have the granularity of table by table because it's what I work with. I also want to have a larger view of the whole repository to control everything that I do. Similar to software, we release the latest version that has sometimes multiple ETLs, and we control that specific version. With code, we want to build in quality. So for data, we have relatively new concept that is on the rise in the market, and we see more and more companies are implementing that. And then these are quality hooks or quality gates. So inside my production, in between the different phases of my ETL, I can have my quality hooks. Ownership model. In the data space, we have data ownership. So different folks are responsible for different tables. I don't know if you have that in your organization. If you do, give thumbs up. And I think you have a question here. Let's take a look. I recently moved a client to a serverless ETL and model inferencing using serverless framework Git S3 Perfect, which reduced AWS cost by 70%. I combined schedule-driven and event-driven methods. This is phenomenal. Saving 70% on cost, this is amazing. Thank you so much for sharing. I'm happy a lot of the methods helped you to reach that. Well done. Maybe you want to share in the chat how you went about that. And there's like, how do you manage version control end-to-end, for example, from source to S3 to Redshift to QuickSight? It's a great question. I can share. We're going to speak about lakeFS that helps us version control our data on S3 specifically. So source ingesting data into the system, I don't have a lot of control of that until I'm actually saving it to my S3. And this is where I work with all the data. So we'll touch on that. This is a good question. Right, and the last one is done means released. In the data world, we often talk about materialized data sets. Your machine learning engineers, your data scientists, analysts, etc. is going to come to us and ask, hey, where is my materialized data set? I don't care about this raw data. I want to work with the gold data, right? The one that's going to give me all the goodness that I need. So let's dive into the conversation, and this is where you asked a really great question. Thank you. Like version control over the whole repository, what does that mean? So let's take a step back to my data version control. So if I have all the tables, I can borrow the concept of Git, because I'm talking about version control. For software, we have Git, GitHub, GitLab. So I can borrow the same concept and say, I already need to hold multiple copies of my software. This is what GitHub does essentially, or kind of copies of my software. So I'm borrowing the same idea in order to control the different versions, in order to manage them. I'll have multiple copies of my data. And I already have questions about when building a data lake, would you keep dev testing and production environments? This is a great question, and I love your question because you're already taking it to the next level and saying, I have my production, I have my data lake, I understand that I need to have data that I'm using for development, data that I'm using for testing, and data that I'm using for production, but it's really the next level that a lot of people are missing. Sometimes they only look at compute, but it seems like it really resonated with you. So you can keep dev testing and production environment in your object store. So depending on the dev environment, where does that live? It can be a local environment, but it's specifically testing or staging. Some people name it staging. You can have it all on the cloud. So when you're running your operations, when you're running your software, CI/CD, you can do all the testing with the relevant data on your cloud. So you can have your environment there. Today, some people already implement development environment in the cloud because they need to do heavier operations. So this is another way to go about it. Actually, I have all the three of them on cloud and have either different buckets or probably different buckets or different policy access. It's better to have them in my production, or different repositories. So my dev repository or my dev dedicated directory within my data, my testing directory, my production directory, and so on. So I hope it helps. It's a great question. Okay, so we know we want to do some data version control, and you can think about the different versions. I can say table 1, table 2, this is my main data, this is what I'm exposing downstream, versus table 1 and table 2 here. This is my V1 of that specific data that enables me to, if I need to revert to a previous version if something bad happens here in my production data. So like I already mentioned before, it really brings me to the idea of Git for data, because this is what we do with software. In Git for data, if we look at it in a different way, we can see that here we have this separation, and we actually started to look at it as branches. Like I have on GitHub, this is my main branch, it's my production branch, and this is a V1 version branch of my production. And this is my whole repo. So my repo holds 2 tables and has delta inside of it. So if I want to do version control in the granularity of a table, I want to control this version or this version. I want to have different versions of these 2, I can. And if I want to have the whole version control over the whole table, all the repositories together, then I'm looking at it in this granularity. So taking it another step into the Git for data approach that enables me later to build a CI/CD for data is I want to be able to revert to a specific version, right? I want to be able to develop in isolation. I want to have my own staging, my own development environment, like the great questions that we just got. So I want to be able to branch out of my current data in order to test something, develop something, troubleshoot sometimes when we have issues in production. So troubleshooting on a specific commit and a specific change of the data. And we can go to a specific commit in time because we mentioned we have the specific log file that we have there. Similar things work when we look at over the whole repository. Second one is another one is atomic updates. If I'm doing updates, we talked about earlier on when we have Parquet and we work with object stores, it doesn't necessarily mean that my table has atomic operation on it because how atomicity works on things like S3 and Azure Blob. And so I need something else to give me that atomicity on top of the files. And for that, I have things like Delta Lake, 2D, Iceberg that enables me the atomicity for a specific table. And now I need to have atomicity for my whole repository. So I have multiple tables and I need atomicity for all of them. So this capabilities is exactly what I need when I think about Git for data. And of course, I reprocess and reproduce, traveling back in time to specific point in time, specific snapshot of all my data, changing something in one of the tables, changing something in a different table, creating some different logic on top of that, and kind of playing it forward to see what got changed. And we have another question following up from the last question. If it is recommended to maintain different repository folders for each environment, do we version control data in each environment? So what happens today in the data engineering world, and again, each company and each R&D is slightly different, really depends on what you need and what you build. A lot of software developers today are copying all their production data from their bucket to another bucket. And this is an operation that takes hours and is highly costly. So to start with, what people are doing to create their staging and development environment, they anyway copy the data. And so you anyway want to have some repositories or folders, because this is what we're going to do as engineers. We want to gain trust in a lot of the software that we build. And because we want to gain trust, and we know there's a lot of challenges that happen specifically with data in production, things, then we copy it to just be safe and getting all the permutations, all the types, all the messy things that happens there, and I can test my logic. So anyway, I want to be able to maintain my repositories and my folders for in general. Do I need to do it for each environment? So I'm saying that with Git for data, I can actually have one repository of multiple tables, and then the branches, I can branch out and say, I'm branching out, I have strong permissions, I cannot merge anything back, so I can enforce permissions. It's only used for branching out and testing some things. And then I can run my test on top of that branch of data that I just branched out of my production. So it's almost like copy, but here we're going to look into a solution that does zero copy, so it's also cost efficient. I hope that answered the question. All right, so we went over Git for data. We understand that now we can operate and do all these exercises at the branch level, so we can start developing a branch strategy and think a little bit out of the box on how we go about that. And there are two open source currently available in the ecosystem. One that I contribute to, so I'll say that I'm a little bit biased. This is lakeFS. And another one that is really, truly great solution, and this is Project Nessie. But like I mentioned, because I'm contributing to lakeFS, I have slight bias towards that, but you're more than welcome to try out both projects and see what works for you in this space. All right, so what does it give me? It gives me the ability to traverse among commits of multiple tables together. Because I'm looking at all the way that I work with data, I can start doing operations like Git, like branches. I can start doing a lot of operations like merging two branches together, creating new branches. Essentially, it's a zero copy of my data, and I can take a commit if I wish to. So if something happened in the past, I did some changes, I can actually go to that commit back in the past. This is what I love calling take a commit. And these are very, very useful because if we want to recover from issues, I have some troubles with a new record that got into my production data. I'm waking up in the middle of the night. I need to start troubleshooting it. But you know what? It's not so severe if we can revert back to a healthy state of the data set, expose that to the customer, wake up in the morning and start operating on that issue and troubleshooting in a more, calm headspace. So this is very useful for that. My merge and all my updates are atomics across all the tables, across all the collections that I work with. Branching enable me with the specific developer or testing environment, which, like you mentioned, someone had a beautiful question here, like how should we go about that? And if I want to take a specific commit back older in time, this is really useful when I need to reproduce machine learning experiments. I've seen a lot of use cases that's related to FDA regulations and things like that, the team had to reproduce the exact experience and show how they're reproducing it. So they had to combine code plus environment plus data. So what I suggest to you is actually that we will stop operating at the file level and start thinking how we can operate at the table and repository level. So start looking at things in a more high-level way. So let's take a look a little bit about branching strategy and some data version control applications. So let's say we want to create a new feature, right? So we oftentimes want to branch out. I have my main stream of data. I'm branching out of that, and I can run my logic. I can direct my Spark application to process the data that exists on that specific feature branch. So imagine that happening in my production. So if something goes wrong, like I'm adding new data into the system, if something goes wrong, I can block it in the merge operation. So you can see it here. So I have my main, I'm branching out, I'm running some new logic, adding some new data. My merge operation actually introduced my quality control gates. It checks that I have the right format of files that I want to write back. It say, okay, you have perfect files in the data that you want to merge back. But oops, somehow along the way, something with the logic, we don't know what happened. Maybe you copied the whole directory. A random CSV was inserted into the system. So here, what's going to happen when I do have my version control, it's going to block me. So this is what I love calling the CI/CD. So it's going to block me. I'm going to use the red color here. It's going to block me on the pre-merge hook, and it's going to raise an alert for me saying, listen, something happened in production. Someone sneaked some CSV files in the directory you always copy. And because all your software, everything, all my ETLs are automated, we're going to block that operation from happening. And all this process enables me a new concept that is called data lifecycle management. So data lifecycle management. We'll just write it here in short. And this is wonderful because I am able to introduce all my CI/CD because I'm starting to think about my data lakes in the way of how we work with Git. Does that make sense? I'm sending you a pulse check. Give me a thumbs up if that makes sense to you. Cool. See, a lot of people get it. There's not a lot of questions. That's very cool. See 2 thumbs down. Maybe you want to ask some questions. I'm more than happy to clarify. Another thing that you raised, this is related to the data governance. So my hooks there, the quality gate that I have, can actually do my data governance here. Am I exposing sensitive user information? Which data did it copy? And anything related here before we're actually exposing downstream to my customers. Is that the right indexing? Is that the right table? Especially with multi-tenancy, we get a lot of issues here. So we want to make sure we're not accidentally exposing, we're not accidentally deleting things that we don't want to delete. Wonderful. All right, so next we're going to start our exercise so you can gain the hands-on experience with all these tools. I suspect some of you have already started because I've seen some questions related to it, and we have another question here. I just want to address it. Can you talk a little bit on how the data repo interact with the source code repo? The data feature branch will most probably correspond to a source code feature branch as well, 100%. And when the source code is merged to master and it runs, it will ideally produce data corresponding to the managed data. 100%. So we can split this process into two. We can have, and I'll just jump here. We can have the, I will take another step back. We can have the CI/CD for code. So you can imagine I have CI/CD here. CI/CD for my source, so this is run, this is part of my software development lifecycle. Here, we're talking about data development lifecycle. And this is something that often happens already inside my production. So when I think about the starting point of my data, the starting point is data in production. Tables that are in production and that are used by downstream. This is my main stream of data. After that, I want to introduce some changes. I want to deploy a new ETL. I want to test that ETL on a separate branch. And this is where it connects back to CI/CD for code. I want to connect, I want to try it out. I want, in part of the CD process, so I have continuous integration. My CD process branches out of my production data, test the new ETL, and then log some response. Give me a green light from a testing, red light from a testing, etc. If I'm doing it only for my CI/CD for code, that means that I'm not merging my data back to production. Because production is production. And what's going to be merged is going to be the code itself. So this is how it helps me with software related to CI/CD, this whole strategy. If I'll take it only to my production, what I can do is every time my ETL, my batch ETL needs to start running and merge some code and ingest some sources, and I'll jump to the next slide. Here we are. So actually this branch is my ETL branch. So forget the feature branch. This is my ETL that runs once every 10 minutes, once every hour. It adds new data in the system, it produces new data, and here I can decide if I want to merge it back into my prod data and expose it downstream. So here, this is a different CI/CD. This is the CI/CD that happens inside my production because it's only CI/CD for the data. So I have my main tables. I'm branching out to run my ETL. I'm adding some new data. I'm merging some streams. And then when I'm happy with the results, I can merge it back into my main stream of data. And here, when I merge back, it might be that I'm overwriting some of the tables that I have or some of the records that I have. So you can think about it like here, we're changing some of the records and then we're merging it back to be exposed downstream. All right, and I hope that helps. And we have another question. With Git maintaining the data in history, even if it's get deleted, how does laws like GDPR data deletion get handled? And this is a really, really good question. So this actually brings me another layer into how lakeFS works, and I don't have it here, but the way that it works, it holds pointers to the data. And because it holds pointers, it's going to write, it's going to do copy on write. So copying all the data only when it does some writing action. So here, for example, adding new data, this is when I do write. I have a writing action happens here. And when I do that writing action, this is when it's this is when GDPR compliance and anything related to it come into play. And because all this permutation and all these branches are managed using lakeFS, so I always know where they are. I always know where to track them. I always know I can run some garbage collection on top of them. So I merge it. I finish that operation completely. I can tell lakeFS, I don't need all the different permutation that you hold anymore for that. Then this is where GDPR data regulation comes in. And this is a best practice. We don't want to hold different versions of the data forever. It really depends on the operations. If we're doing it for quality control, I'm not necessarily always want to hold all the permutation of all the running ETLs forever. It might be that every 10 ETLs, 7 ETLs, depending on how often I run them, I want to save it and I want to be able to revert to a specific point in time. But definitely not if I'm running them every 5 minutes. I don't want to hold endless versions, even if it's zero carbon versions of that specific data, especially when I work with data that relates to GDPR. So I hope it helped. And PII is a really, really important topic. We have one of our users, one of the lakeFS users shared in the Slack that they're using lakeFS to remove PII because one of the challenges they had is they needed to run PII checkups and deletion and on all their data lake, and they were very afraid to accidentally delete the wrong files. Makes sense, right? And so they leveraged this technique of this strategy of branching out, doing the deletion of the branches, and then here inside the merge hook, the quality assurance, they did it manually because it's a very sensitive part and they only ran it once. But here in the merge hook, they tested to make sure they didn't accidentally delete the data that they needed. They ran some automation against it, but there was humans involved in the process. And after the human involved in the process decided that it looks good, then they merged it back. And it was one operation that they did, and they leveraged, they have lakeFS installed in their production system anyway, but it was one of the PII process that they ran. And once they did that, it's basically easier to automate the process early on where you're just injecting data into the system.
I'm sorry.
Cool. Any more questions? Anything comes up? Can only see the shared screen. Oh, sorry. I apologize for that. I hope it's better now. All right, exercise. So next section is actually, we're going to go through, there's a challenge waiting for you. So you can start your lakeFS challenge here. What I am actually going to do, I'm going to go over the solution with you. So this is a quiet time for you to do the challenge and gain some hands-on experience and ask questions. And we will be here back in about 20 minutes, something like that. And if you go to GitHub, Treeverse, you'll see here. There we are. So you can see the open source right here, and there's a lot of different information related to it. You can also see the code of conduct and the license and the README. And what I want to show you is actually how do you get started. So what I provided you with a Docker Compose solution that already brings up all the services that you need in order to have Jupyter built in and lakeFS built in. So this is how we went about that. But if you want to continue exploring, you can run lakeFS on its own using this. Or if you wish, you can jump right into an existing instance of lakeFS Playground. And here inside the lakeFS Playground, you can actually already connect your cloud storage to the lakeFS Playground and start exploring. So you don't have to manage it on your own. You don't have to install. You don't have to use Docker. You can immediately jump into the Playground itself. If you're more adventurous, and we have a lot of DevOps here, here is how you can deploy it to Kubernetes. Or if you wish, you can also use the binary itself. All right, and since we have lakeFS already up and running, we can start exploring. So what I have here, I have my existing repository, and if I want to, I can actually create a new repository and calling it test, and some local. Oh, I only have S3 options here, so I won't create anything. But basically, giving one of my S3 buckets. So let's find a random S3 bucket, open to public. Let's see if we can quickly find some S3 bucket open to public data set. Sometimes AWS will publish existing buckets that all we have to do is actually direct them there. See usage example, folding home, molecular. I don't see anything interesting here, and that's for search, but this is definitely one of the things I can already start doing. Anyhow, here's where I'm going to give my my cloud storage essentially, and I can already start working on it. For the sake of this exercise, we won't do that. We're going to use what we already have here available. So I have my data sets. I can also import more data if I wish to. So let's say I want to bring in more data sets. I can import it directly from here and put it in my destination. And then it's going to write it into a specific branch called main imported, underscore main imported, and I can add my commit message. I can also upload files from my upload specific object, or if it was configured to my local storage, I would be able to upload things from here. All right, if I did any changes to the different branches, which I didn't, but let's say we want to introduce some changes, I can, and then I will see it immediately here. So let's bring up our solution for a second, and let's restart our kernel, run this, run this. You can see that I have a lot of data already in it. Let's do kernel, run all. I can go here into my objects, look over the things that I have here, and for example, take one of the actions and say, I want to delete this file, just for the sake of deleting, okay? All right, I deleted this file doesn't exist. When I'm going into my uncommitted changes, it will show up as an action that I took. I didn't commit these changes specifically. And I still have what was changed here. And what it's going to tell me is inside this hierarchy of files, I have this specific file that I deleted. And this is the actions that I took. It was removed. And here I can see show changes, and the change is only going to give me what the change in terms of size, so 3.5 megabyte in size was removed, and I can also revert these changes. So after I did a specific action, if it was in code or from the UI or from the CLI, I can immediately go back and revert these changes. I can also commit and say deleted file, add some metadata field. Let's say deleted. Doesn't mean anything, but for the sake of the exercise, and that I won't see any changes here anymore. And inside my commit, it's kind of like my auditing. It's everything that is being tracked. I can see that things were already deleted. So that specific thing was deleted. View commit actions runs, copy, URI, and browse different objects in these commits. And then when I look into branches, I can actually compare the different branches. And because I did an action on top of these branches, is now the improved data was already different because part of our exercise was actually to find the differences. But you can already see that this specific file was deleted. So this was originally in both of the branches, but here you can see that this file was deleted. And I can decide, I can look at the changes, I can decide if I want to merge, I can, refresh if anything changes inside my data. So that gives me a lot of control when I'm looking into what is really happening within my data. And if I want to pick a merge specifically, this is where I'm taking a merge. I have an idea, I can take the merge and I can revert back to what happened in the past. I can also attach it to specific actions. I didn't do anything here, but this is where my quality hooks, quality gates come to play. So I can create a dedicated script inside my repository, and this department, lakeFS will know that means it needs to connect to a specific action, to specific quality hooks, in order to take advantage and truly build the CI/CD for data. I also have retention policy that I can configure, like we mentioned, for my GDPR and a lot of the PII data. I want to delete some of the branches. I don't want to keep these pointers. I don't want to keep stale files. So I can define my garbage collection policy that is going to make sure that I am deleting my previous and some history. So only the objects that I need are being kept. And I can also add branches protection rules. So if I'm designing all my infrastructure and all my data lake to leverage that, and I want to be able to separate from my main production branch from my testing, so testing doesn't merge data to production ever, it just gives me the final result if that logic is good or not, and actually does what I wanted to do on top of my data, then I can define my branch protection rules. This is where I'm going to go in and say, I can only branch out, I cannot merge back. Or only specific users, it really depends on what I want to do, but only branching out without the capabilities of merging the data. So I can actually leverage that as part of my code CI/CD. So my staging environment is actually a zero copy of my production data, because I developed a dedicated branching policy to make sure it adheres to that operation. So that is makes it a very, very strong tool for us to take advantage and really build robust CI/CD for code in terms of testing and validation of our logic. So it's a good opportunity to truly develop the trust that we need in the code that we just developed. Another branch protection that I've seen a lot of community members in the lakeFS community use, that's for different users. So for example, if I'm developing data systems to serve machine learning practitioners, oftentimes I don't want them to merge back to production, or I want them to work on their own, sometimes repository, on their own branches. So this is another very strong use cases for us as we're managing your data. We're thinking through governance, quality, what is being exposed. And then a great thing to take advantage of And there's a lot of other protection rules that, you can think about. It's what's nice about it is it's generic enough so we can actually start playing and working with it. Another strong features is tag. Someone said here today beautifully is, I have my version control for code, I have my version control for data, and how do I combine these? So one of the things to actually combine these is through tags. So let me make it bigger for you. So to simplify it, tags are a nice way to give names to things. So we can combine the code version control together with the data version control through tags. So I can actually mark some release this data used to, this version of data is used to test this code version, and we're testing them together. And that's it. This is what produced the results that I see in my tests. Green, go, no go, green, red, really depends on the colors you love. But it gives me this capabilities as well. All right, so this is lakeFS, very simple to. All right, awesome, thank you, you're great, it's amazing. Okay, so what does a typical environment looks like? And this one changes definitely from each one of us. So like I mentioned, we have all these policies. So often what I want to do, I want to have my production branch saved, secured with very strong policies that everyone that interacts with my lakeFS service and my repository have little and very specific access to my main production branch, right? So I'll have a lot of the workloads here, and like you see, I have this beautiful lock on my main. So it does a lot of computation. Here there is some merging happening, but again, it has to stand with the policy. So for example, if I have a dirty ingest, I'm now ingesting data from a new source into the system. That happens a lot. Sometimes we need to support, I don't know, tens or hundreds of sources of information being ingested into the system. We don't always control that, but we need to do that so we can do it on a separate branch. So here I have a 0 copy of all my production data that I'm merging with my dirty ingest branch. I can merge it here. I can do another ways to do some commits. I'll be able to revert if I need here within that. And only after I did this commit, I can decide if to merge or not to merge back. And this is, again, according to my policy, according to what I think is right. So how would a staging or developer experimentation branch would look like? Developer environment would look like where I have a wall here. This data goes nowhere. It doesn't go back into my production environment. I am branching out, right? I got my branch, I branched out of my production system. I'm running my code here on top of this data. So I'm telling my code, please run on this data, this URL, this specific branch. And then I commit, I do all the other things that I do. But here, this is very clear. No one trespass this line, essentially. This is where it ends. This is where I have a go, no go for my code. So this is my developer experimentation branch, or if you will, machine learning, data scientist experimentation branch, BI analytics experimentation branch, and so on. So this is one typical look at the environment. Any questions so far? I know usually here there's a lot of questions that comes up. Okay, so I understand everything, you're clear, and you fully understand what that means. That's awesome. A second one is part of my consistency, cross data sets, cross collection consistency. So similar to previous what we said, I have a lock here. I'm locking my production branch. No one can touch it. No one can do anything with it. And then I'm starting to develop my policies. And my policy means I'm bringing, and my workflow is I'm bringing a lot of different streams into the system. I want to know if this stream is good, it's not good, or whatever. For that, I need my ingestion branch. So my ingestion branch here is critical because I want to know what I'm ingesting into the system, if it's good, if it's not. So this is a copy. This is already my first copy of my production data here. And here, this is my updated copy of production data after I already did a merge with a dirty ingest branch. So I already have a new view of my production data after merging one data with my production and getting a result. Second one, I'm getting in another stream into the system. Like I mentioned, sometimes when we develop our data systems, we need to be able to support endless amount of streams. This is sometimes being automated. We don't necessarily know or control the streams that are being ingested into our system, and we will need to build it in a way that it's scalable, efficient, and secure. So I'm going to ingest another stream of data here into my branch because this is what my ETL logic does. It ingests and merge all this wonderful data sets together. And here I need to make a decision to merge or not to merge. This is where I have two different steps that I can integrate into the system, and I can say, do I want to merge all this dirty ingested streams? Yes or no? And you can understand from the name, because I call them dirty, I maybe don't want to merge it, but maybe I do. Who knows? It really depends on what it is that we're doing. And here, the nice things about it is because I did a merge operation, a join operation of multiple data sets, I can travel back in time over the whole repository that got changed. So here I have two tables, and these two tables produce their third table. And I want to be able to travel back on time over the whole repositories together. So this is where the cross-collection consistency or multi-pit tables transaction consistency comes into play. And this is something that my object stores and my table formats don't give me out of the box. Because my table formats handles the granularity of one table at a time. So here. But they don't handle the granularity of all the tables together. So it's always a different workload that we want to be able to support both of them. So actually combining a table format together with repository data version control is really useful and gives me all the power and the resiliency that I need. And after that, I can decide if I want to merge or decide if I want to expose. And also here we see the dev testing environment again, just in case if we need that also as part of the cross-collection consistency work. Let's take a look at a long-running ETL in isolation. A lot of our workload would be long-running ETLs. And these long-running ETLs can fail. Give me thumbs up if you ever needed to handle an ETL that runs for a long time and it failed in production. So sending you a pulse check, let me know if you ever need to handle long-running ETLs in production that failed on you, unfortunately. All right. all right. We get some thumbs up. That's nice. That's nice. All right. So many times, a lot of the workloads, some of the workloads that we have are long-running ETL. These are the constant workloads that runs inside my production. Oftentimes, we don't want to change them a lot. This is legacy code. You need to have them. They do the work. And we're very much afraid of changing that, and for a good reason. And that means that I can also implement it in my branching strategy. So come again, if I have my main branch, which is protected and secure, I can have my ETL running, and then this is a process you can automate because of the clients that enables us to automate these. I can automate branching out. And for every iteration on the data sets that is, or multiple data sets or repository that this ETL is doing, I'm doing a commit. And this commit is really critical because if something happened along the lines, I need to troubleshoot, I need to revert, I need to cut some, find some issues that happened back in time during the process of this ETL, I can actually go back commit by commit and start troubleshooting, which is very different than what most of us are used to today. Today, we have to try and compute on ourselves, how did we reach that data stage? What happened along the lines? While this is great, it's very hard for us to do that reverse engineering on our own, where we're dealing with a lot of data and also a lot of different permutations that the data set goes through. So if something happened, I can easily revert to one of the commits and start troubleshooting. I can also revert to one of the commits, drop some record that makes my life, that challenged my production, and then continue the operations back. So it's a very, very strong tool when we're running ETL in isolation, so it gives us that commit. And maybe it reminds you of Spark checkpoints. Does anyone here familiar knows about Spark checkpoints? Yeah, so this mechanism is very similar to Spark checkpoints, although Spark checkpoints are used for a specific data frame. So I can checkpoint the state of my data frame and save it back to this, because my data frame essentially are inside my RAM memory, right? They're in memory. I can checkpoint my whole data set using this mini commits along the way. So again, this is a very powerful tool that enables us to go beyond one data set, beyond one data frame, and really leverage and really start doing troubleshooting or revert if we need to. And always as a best practice along this line, after we're doing a couple of commits, it's actually a good idea to merge back to production, of course, when everything is good, and then continuing maybe another branch if we wish to for the same logic of the ETL or for a new logic of the ETL. Sometimes we want to split it, sometimes not. But you can imagine this is ETL 1. ETL 1, or the first run, and this is my ETL, okay, second run. So it can be the same logic, although it runs on different versions of the data and different times, because my ETLs runs once an hour, for example. All right, so let's combine a lot of the capabilities. We can always split it into 3 different things that we do with software. One is for development purposes, and you've seen how easy it is to branch out for the sake of development purposes and build the policies and the security in order to block merging back to production. Second one, if we wish to use it for what we call deployment, so leveraging the hooks and quality gates. And the third one is my production. If anything happens with the long-running ETL, I can always revert back, troubleshoot, and do everything that I need. Some of the nice outcomes for that, and I know that not a lot of us, many times we are being asked to cut cost of our infrastructure, of our cloud, etc. So something in between 20 to 80% of our storage, we're saving on our storage, so storage cost reduction. It speeds up our development process. So double data ops efficiency, 100%, also for data governance, data quality, and software engineers gaining control and getting more comfortable with their code. And 99% faster recovery from production outages. If something happened to my data because of my logic, I can always revert, which is really, really important. And I mentioned that it has a zero copy mechanism built in, and this is because of the data structure and the brains behind it. And I invite you to read in the documentation if you want to dig deeper into it. There's a lot of really good, really interesting brain behind this that comes from the data model and how it was built and the data structure. This was inspired by a lot of work that comes in the world of databases. So very, very interesting to understand how we connect the keys to the actual values and build the identity that represent a value record for lakeFS or file, a file got changed, and so on. Under the hood, it uses Merkle tree. Merkle tree is a cryptographic tree. If you don't know, it's also used in a lot of tools by Oracle and other databases. And the beauty all around that is Merkle tree help us know if we use it correctly, we can know if a file got changed. So we don't care about indexing at that point. It's not a B+ tree. It's not type of this world, but we only care if something gets changed in our storage. And this is the beauty of Merkle tree. It's very efficient. It gives a different solution, leveraging trees. And it's really demonstrate how a lot of us in the industry think out of the box in order to leverage the data structure, the basic data structures like trees, to get tasks done. So if you're looking into this world and you're working as a data engineer, it's good to be familiar with Merkle tree and what it means. So to give a little bit more information around the data structure, there's some commit ID that attached to everything that we do. Like you've seen, I can my file that I deleted wasn't committed, and then I committed it, so it got some commit ID. And then I'm entering it into my table inside my meta range. So each one of my commits essentially are going to live inside some range, and I have my meta range, and it has range ID. So I have two tables where the range ID is actually pointing to my identity within the range, and there I'm holding a hash on top of the content, the tags, and the